So we're recording now.
Hello guys, welcome to a new vlog.
Jayag, yes, we have Yusa with us today, and Yusa is gonna be our dummy student. He's our dummy student because he's very stupid. Like, get it, dummy. We're gonna be doing double slit. Take a single slit, double slit diffraction and interference. All right?
Okay.
Take a So I'll be explaining this to Yusa, who is a very not so smart student, but we'll just forgive that. So, acha, ये दिबो नाकि double slit pattern putan দিবো নাকি?
I don't know.
হ্যাঁ,
I don't know.
যেগুলো একটু বলবো নাকি?
I don't know. Just explain it to me as if like when you're explaining to someone who needs to know all this, like কিছু জানে না, but like he needs to go all over. মানে all
একদম
through.
বেসিক্স থেকে না?
হ্যাঁ.
ওকে ফাইন, ঠিক আছে, তাহলে এটা থাকুক এখানে, উইল refer to it every now and then. ঠিক আছে না? Is your phone on silent? Okay, are you talking?
Should talk less. আমি একটু কম কথা বলবো.
But like you should be around, okay, not be non-existent. Okay, let's start. So first of all, we're going to be talking about double slit diffraction. So to understand double slit diffraction, you have to understand two things. Number one, you have to understand diffraction, and number two, what you have to understand is interference. Interference, specifically superposition. Do not comment about my handwriting. Thank you, Yusuf. So what? Anyway, we're going to talk about diffraction first. So diffraction is something that you've learned from your O levels, right, Yusa?
Yes.
Okay, good. So it's basically the spreading of a wave when it passes through a gap equal to its wavelength, or less, or when it passes over an edge. For example, if you have this wave and it passes over this edge, what's going to happen is it won't diffract overall, just that's supposed to be straight, and this edge will diffract. Okay, that's a horrible diagram, but basically diffracts here, but on this side it goes straight without diffracting. So diffraction not only happens in gaps, but it also happens when you cover across edges.
Okay, so
Yes, what?
is this why we can see better when we squint our eyes?
Partly, yes. So that's more to do with the pinhole camera, but yes. So basically the point is that diffraction is the spreading of a wave, which is due to the gap being equal to the wavelength. Really simple stuff. And what is interference? Interference is when you have two or more waves meeting at a point, and what you see is the resultant of these waves. So for example, if you have a wave which looks like this, artsy wave, and you have another wave which looks like this, and they meet at the same point, what happens is they add up. This adding up is called constructive interference. So if I was to draw that, that would be basically, I'm trying to draw a better diagram now. So basically a wave like this and a wave like this meet. As a result, what you're going to see is a wave which is twice the amplitude. That's because their amplitudes add up, right? And the other possibility is this thing called destructive interference. So let's call this constructive interference. Destructive interference. And the opposite of this is this thing called destructive interference. You've used up my space. It's alright, don't try to touch me. So destructive interference is basically what?
It's the opposite.
Yes, basically you have waves which meet like this. So these, when they meet, they're overlapping perfectly. These are called in phase, right? When they perfectly overlap and meet. And if they meet like this, basically half a wave difference between them, so that you have this maximum meeting a minimum. This is called antiphase, right? And what antiphase leads to is this thing where the whole wave just becomes absolutely flat. That's because this is being cancelled out by this is being cancelled out by this. Got it?
Okay.
So yes, that's the basic concept of interference that we're going to need. Right, now let's go into using these two concepts to explain double slit diffraction. So first of all, say we have a single slit and we have a wave passing through the single slit, so you get a diffraction pattern.
Yeah.
Then say what we do is we take another pair of slits, and these waves which diffracted first diffract again here. And why we're first passing it through a single slit is so that the same wave at the same phase reach these 2 points, right? So it's basically literally the same wave at these 2 points. So basically we have this diffracting here, and we have this wave diffracting here. And you might assume that the pattern that you should get for these two interfering should be pattern like this. The height of the graph represents the brightness. So basically this would be the brightness due to this slit, right? And from this slit you'd get something which is more like similar to this, just like this, right? This is basically two of single slits, but that's not what you get. You get none of this. You get this really weird pattern actually, which is basically, if this is the center between the two slits, you get this really bright place here, and then suddenly a dark place, and then another bright place, then a dark place, then a bright place, then a dark place, like this. And you get the same thing on the other side also, like a bright place and a dark place. So the question is, how do we actually get this pattern, right? These bright and dark spots. So one of the things you first have to understand is you have to look at this from a mathematical or a geometric perspective. So this is what we're going to do here now. So we have these two slits and we have a screen, and basically what I'm going to do is I'm going to draw different paths from the slits to different points on the screen. So what I do now is an isosceles triangle, right? Basically the length of this line is equal to the length of this line. So say I start drawing waves here. I draw one wave, two waves, three waves, four waves, five waves, right? And I draw the same thing here. It should be one wave, two waves, three waves, four waves, five waves. So the waves which meet here are basically what? If we see the last cycle, you will see it's something like a wave like this, say from slit 1, and from slit 2 you get exactly the same wave again, right?
Yeah.
So they're meeting in phase.
Yeah, so like constructive interference.
Yes, you get constructive interference, which leads to what?
Bright image.
Yes, basically you get a bright spot here. So this is a bright spot, right? I'm trying to draw this as nicely as I can, not as artsy as you are, but trying my best. So I'll just move this to this side so it's a little better to understand. Now let's say we take this point here, right? I don't know exactly the length of the point, but we'll just use it for our assumption. So say this is the path from this side. Oh, I don't want that, go away. And from here, say I have this distance. Now assuming it matches perfectly, I hope tomar chulkani uthe na. So ekhan theke say we have one wave, two waves. I'm trying to draw the same thing, three waves, four waves, alright? And from this side say we have one wave, two waves, three waves, and see how we can't have complete four waves, we have 3.5 waves, right? So if we look at the last part of the waves which meet here, for one wave, for the wave from S2, it's basically this, right? And from the wave for S1, it's the opposite, like this. So what do you get? You don't get a bright spot anymore. You get a dark spot because you got what? Destructive
interference.
Yes. So the same thing would happen on this side also, right? Because it's a triangle having those same lengths.
Yeah.
So what we could do is this whole idea, we could write it down nicely here. For example, we can say there's a path difference, right? And what does the path difference lead to? It leads to a phase difference. And what does the phase difference lead to?
Difference in brightness throughout the whole
basically
screen.
And a resulting interference, right?
Yeah.
Okay. So what's the path difference here? At this point the path difference is 0 lambda. We're going to talk about all path differences in lambda.
Okay.
Right? So 0 lambda, because as you saw this was 4 lambda, this was 4 lambda, oh sorry, 5 lambda, 5 lambda, right? Here we saw one of them was 4.5 lambda, sorry, 4 lambda and 3.5, right?
Yeah.
So the path difference here was 0 lambda, so it led to a phase difference of 0 degrees, and that leads to what? Constructive interference, right? We'll write a C for that, and that led to what? A bright spot, right? So this is basically that spot. What did we see here? A path difference of half lambda, right? Because this was 4 and this was 3.5. So path difference of half lambda, which leads to a phase difference of how much? Half of the cycle. Half of the cycle in degrees is how much?
180 degrees. Yeah.
Which leads to destructive interference, and destructive interference leads to a dark area. Does that make sense?
Yeah.
Right. And obviously we're going to get the same thing on this side, half lambda, 180 degrees, and hence this is also going to be a dark fringe, right? Now, interestingly, something happens. If we go further out, right, we're taking this point now, and I'm drawing another line from S1. Oh my god, stop, go away. I'm not going to draw any more waves here, but basically what's going to happen is from this side you might get say 5 lambda, and from this side you're going to get 4 lambda, Alright? So what's going to happen is you have a phase difference of exactly 1 lambda.
So they're in phase.
So they're back into phase again. The phase difference is 360 degrees, which is effectively back to 0 degrees. So you get constructive interference, which is basically a bright spot again. And if you go further down, this thing will continue to progress. So it's going to be 0.
You'll get a pattern.
Exactly, half, the upper 1, then you're going to get a 1.5, which is 360 plus 180, right? Which is basically destructive, so it's going to be dark. Next point is going to be 2 lambda, so that's going to be 360 plus 360, right? I'm just breaking this down so that it makes sense easily, which is constructive again, it's a bright spot. So the pattern that you would eventually get, this is representing half lambda, bright spot here 1 lambda, dark spot half lambda, and then say this is another bright spot. So the pattern you'd get is basically bright, then dark, bright, then dark, then bright again, and this would continue. And it's going to be the same on this side, bright, then dark, bright, then dark, and so on and so forth, right? You get it?
Yeah.
So that's pretty much it. So if we actually take a second and see a couple of patterns that we have, or we've pulled a few out from Google, you'll see that all of the designs and all of the diagrams here explain the exact same thing. There's an interesting thing here. We have this nice pattern here, horrible resolution. So jogonno aspect, but I hope it's going to work. So yes, using my pen, you'll see that I'll use a different color. I'll use, say, red. So what happens is that you get this line along here where all of the crests meet with crests, right? So this is basically the path of constructive interference. Same thing happens here, crests meet with crests, crests meet with crests. So yes, this is basically the line along which you get constructive interference, right? If there were more arrows, you'd get them here too. More lines, wavefronts, they'd intersect. And you also have the same thing along here, right? So what happens is, this meets with the bright spots, right? And মাঝখান দিয়ে এই যে জায়গাগুলা, এখানে you're getting the crest of one wave and the trough of another, crest of one wave, trough of another, right?
Yeah.
So এটা দিয়ে you get destructive interference. That's why this region is dark here, right? So this is another way of explaining the same exact idea, but without the mathematics. It's basically with the idea itself, right? So do you get the whole concept of double slit diffraction and how we get dark and bright fringes?
Yes.
Okay, beautiful. So the next thing we need to understand is how is this relevant to the mathematics related to it. So that would need us to go into a specific equation, a very easy and a very specific equation. The equation goes as lambda is equal to ax by d. You'll come across this in different forms. It might be xs by d or blah blah blah, but basically if you know what each one represents, then you'll understand it. So lambda is basically the wavelength of the wave which is incident on the double slits, right? So basically age of wave ter, this wave's wavelength, this is lambda. Then we have a or s, slit separation. That's basically the distance from the midpoint of one slit to the midpoint of the other slit. It is not if I draw the slits really like zoomed in, say like this, x is going to be, or sorry, s is going to be this distance, not this distance.
Yeah.
All right, it's not this, it's not that, it's the midpoint of one slit to the other. And why am I putting emphasis on this is because there's these situations where they keep one slit narrow and another slit really wide. So how are we going to measure the difference here? It's going to be from here to here. Get it?
Okay.
So that's a. X is fringe separation. Fringes are basically, you have the bright spots which are called maximas or fringes, and you have the dark spots which are called minimas or dark fringes. So the distance from one maxima to the next is basically x, right? So this is x. You can think of this to this is also x. Please again.
So like minimas to minimas is
also x. Yes, correct. Usually we consider x to be from one maximum to the next, and usually we take it from the central maxima to the first peripheral maxima, because that value is considered to be the most closest to your actual value of x. That's because as the screen is flat, the pattern does have some
deviation,
stretching. If you had a curved screen, you'd get an equal pattern, but we don't have a curved screen. So that's basically, we consider the closest one to be the right value. And d is basically the perpendicular distance from the slits to the screen on which the light is falling to create the pattern. So here, what they want you to do the most is they kind of love asking this specific question in this pattern. If we come back here and we bring in the equation lambda is equal to ax by d. This is d, this distance, all right? lambda is the wavelength, this slit separation is basically A, and this maxima to this maxima would be X. So what they love asking is how, if you change different parameters in the pattern, in the setup, how would it affect the fringe separation X? So what I strongly recommend every time is you rearrange the equation into X is equal to lambda d by A. Right now life becomes much easier. So what do we know? It's directly proportional to lambda and d. So basically, if we increase the wavelength, what's going to happen to the fringe separation? It will increase. If we increase the distance from the slits to the screen, then the fringe separation will also increase. That's pretty much like a projector, right? The further you move the projector, the bigger the screen becomes. And what happens if you decrease the slit separation? X increases. To decrease X, you'd have to bring the slits closer to each other. Does that make sense?
It does.
Pretty much that's it.
What happens if you do curve the screen?
You
the
get
intensities will
yes, it's going to become
same.
evenly spaced, and also the separation X will remain constant throughout.
Okay, but will the intensity of the maximas be same?
In some diagrams they do represent it to be the same, but there's a thing called a diffraction envelope. That's basically the whole thing fits within this envelope of diffraction, right? Like the single slit pattern. Slowly it does become weaker on the sides, even if it's a curved screen. So curved screens are mainly used to measure the value of X accurately.
Achha.
But it won't be so low. Obviously it's going to be a little more because the distance to the screens are closer. So that's the most common question that they ask. The next question that they ask is what's going to happen if you increase the brightness entering the experiment, basically the amplitude of the light entering into the experiment. So nothing really significant happens except for the maximas become brighter. So let's give this a different color so that you can easily understand it. Let's make it red. So the maximas, what happens is they become brighter, but you have complete destructive interference at the minima still, so they remain completely dark. So you get a pattern like this. This would be the result if you put more light into the experiment. And the second thing that they love asking is if they make one of the slits larger and keep one slit the same size. What this results in is incomplete destructive interference. So the bright fringes do become brighter, but the dark fringes don't become complete destructive interference. You have this little bit of light still left. Why? That's because you have more light coming from one slit and less light, yeah, exactly, less light coming from the other. So what this leads to is a little bit of remaining interference, right? Remaining light. So you get incomplete destructive interference. How would you describe this? You say the bright fringes become brighter and the dark fringes also become brighter. And if they just increase both slits, the width of both slits or the brightness of both slits,
by the same
you just say that yes, that the bright slits become brighter and the dark slits still remain completely dark.
The same, yeah.
Yes. So that's it. And other than that, they really don't have much to ask from that. Sometimes they do ask how to do this with sound. If you want to do this with sound, instead of little slits, you have little microphones here. You can do this with microwaves. You can do it with literally any wave which interferes. As long as they're waves, they will interfere, which means you can create a double slit diffraction pattern.
How do you do it with sound? Automatically?
You keep just two speakers, a certain distance, and usually they have something like, a person, and the person walks from this end to the other end. This is obviously a much larger area, right? Because the wavelength's bigger. So as they walk, they hear this changing intensity from loud to less loud, right? Loud to quiet, loud to quiet, loud to quiet, and that's basically them moving from one maxima to the next and minimas in between. So pretty much that's it. That's double slit diffraction for you. I don't think there's much left. Let's just go into the syllabus so that we are sure that we covered all of the points. Two slits. Understand the terms interference and coherence. Coherence is basically constant phase difference. Basically, when I was drawing the waves, we were drawing waves which had constant phase difference, right? Or constant wavelength. Show an understanding of experiments that demonstrate two source interference using water ripples, light, and microwaves. So we showed the ones with light, and the same exact behavior seen in water ripples and also in microwaves. If you want to see one with light, it's very easy. Sorry, with water, it's very easy. All you need to do is if you come across, if you just Google double slit diffraction, you're going to see different patterns. So there's this double slit diffraction in which if you use water, for example, is that water? That's not water. That's just blue light, blue waves. Do you see any with water?
But
oh,
it's going to be something like this.
Yes. Basically, you get choppy water and calm water. Basically, this isn't water either, but still we can use this to explain it. You'll get these bands. This is basically constructive, this is constructive, this is constructive, and the dark area between represents destructive interference. Alright, so that's that. And then what else do we have? Understand conditions require two source interference fringes are to be observed. So basically the waves have to be the same type, they have to be on the same plane and similar frequencies obviously, and hence that's when you can see interference, and they have to be meeting at a point. Recall and solve problems using equation lambda is equal to ax by d for double slit interference. I hope you got that. So that's pretty much it. And yes, so in quick summary, I'll just quickly summarize all the points that we said so that it's easy to understand. So first of all, what I said was light or any other wave can interfere. This interference can be of different types. It can be constructive or destructive. It's constructive when they meet in phase, and it's destructive when they meet in antiphase. The next thing that I said was, or before that actually, I said there's this concept of diffraction which causes a wave to spread out when it passes through a gap equal to or smaller than its wavelength. And these are the two concepts that we'll need to work with, interference and diffraction. Then I showed that we have this double slit diffraction. We end up getting a pattern very different from what we actually expected. Two separate diffractions. Instead of that, we get this addition, which is a weird pattern. And then we went into the reasoning and the explanation behind why we get this pattern, and also we saw a bit of the equations and the mathematics related to getting this sort of pattern. So you basically get bright spots wherever the wavelength is a whole value of n. So basically we can call these points where the value is n lambda, right? So n lambda, the next one here would be n lambda, right? This is also n lambda where n is 1, this was n is 0, this is again n is 2. And we got these points where it's basically n lambda plus half lambda, right? So basically this is just n is 0, so it's half lambda. Then this is n is 1, so you get 1.5 lambda, then 2.5 lambda, right? So these are the differences that we get mathematically. And eventually we saw that there's an equation lambda is equal to ax by d, which can be used to find different variables, and you can also find the wavelength with it. So from here, x is the fringe separation, a is the slit separation, d is the distance between the slits and the screen, and lambda is the wavelength. So yeah, that's it. And if you rearrange the equation, you can turn x into the subject of the formula, make stuff easy. Alright, so that's that. Yusa, did you get all of that?
Yeah.
Any questions? No questions? You sure?
Yeah.
Okay. Thank you. So we're done with double slit diffraction.